Okay, so thank you for coming. Thanks for braving the game day traffic here. We're excited about lots of things going on today. And one of them is coming to this Inspire Me or Inspire Any seminar. We're combining today with electrical engineering and also computer science. So thanks for everybody for coming and being a part of this exciting presentation for us. I'm going to introduce my speaker, who I think some of you may know, Dan Isla, who was a 2009 graduate from electrical engineering here at Boise State. I first knew Dan when we were going through a microgravity project together the very first one back in 2009. So he was on the very first team that went up there and flew on the microgravity airplane. So after that, he went on to do a few other things, like working for JPL and getting involved in some interplanetary robotic research. And so I'm going to let him tell you about that because that's a little bit over my head. So, all right. Well, thanks for coming and welcome, Dan.
Thank you very much, Don, and thanks everyone for coming out here. It's really a pleasure to be back to my alma mater. I don't know how many people in the industry get to do this, so it's definitely an honor to be here. So today I want to share with you kind of my journey, the narrative of how I went from working and earning my degree here at Boise State to working on interplanetary missions such as the Mars Science Laboratory, Curiosity Rover. And so and really also help you share with you some of the tools and techniques I've learned along the way that might make you a more successful engineer in the workplace when you do graduate. So I've got some slides, some pictures, and hopefully we'll have some fun and learn a few things along the way. So back in 2005, I joined Boise State and entered directly into the engineering department. I had worked in industry at HP as a tester for 3 years before that. So I was kind of a non-traditional student. I didn't go right out of high school. But I did grow up here in Boise. Was homeschooled for most of my time, and that actually let me kind of focus on a lot of the things like, what do I want to do with my life? And so working at HP was a great experience to see, like, what is this engineering thing, and is it really what I want to do? I know I love computers. I love things that were very technical. I love taking things apart. And so shortly after my time ended at HP, it was a natural fit to go and get my degrees. Like, now I knew what I want to do. So I came into Boise State pretty focused, and like I knew I wanted to do something. I knew what, and I felt like I fit in here. I knew it was like, this is the community of nerds that I was definitely one of. So my junior year here at Boise State, I interned at the Jet Propulsion Lab. This was a 10-week experience. I didn't even know what really JPL was until a fellow student told me, hey, I did an internship last year, and it was awesome. And it was at JPL. I'm like, what's this JPL? And how do I do that? Because it sounds awesome. So I was able to do that. I applied through Space Grant and did a 10-week internship. Got to fly a spacecraft called Epoxy. We were taking pictures of exoplanets. And it was an amazing experience. I got to see the laboratory down in Pasadena, and it inspired me enough to take the offer that I received at the end of the internship. So after that, I came back to Boise State and worked with Barbara Morgan on the very first microgravity team here at Boise. This was something that I had just heard about, and I didn't know anything about it. I was just entering my senior year, and I was like, okay, what can I do for my senior project? We had a few options, and this sounded like the most exciting one. There's a way to collaborate with NASA. You get to fly in the zero-G plane. I know a lot of you guys have probably heard about that since its inception. I hear it's been an amazing legacy that's upheld through the university. So I'm very proud to be a part of that experience, and it really gave me a more solid foundation in systems engineering, which is what I was hired on as at JPL. So when I arrived at JPL in 2009, shortly after graduating, I got to work on these robotic explorers, namely the big one there, Curiosity. And JPL has often been called the Disneyland for nerds, which is kind of funny because it really is a fun place to work. It's very diverse, and actually is not that far from the real Disneyland. Go ahead. So these are some of the robotic explorers that we work on, and next I'm going to show you a short video of some of the robotic explorers over the years that JPL has had a part in. And this is actually a true statement. So, kind of fun building a colony of non-sentient robots that we know of that can go and explore the world. So being part of that is amazing. So let's learn a little bit more about what JPL's done.
Extraordinary men and women of NASA in our Jet Propulsion Laboratory. Right now, the wheels of curiosity have begun to blaze the trail for human footprints on Mars.
Well, today on Mars, history was made on Earth. The successful landing of Curiosity will stand as an American point of pride far into the future.
I just want to call and say congratulations to the entire Mars Science Laboratory team and really all of JPL. You guys should be remarkably proud.
A fun video of just the awe of what we do at JPL and the missions that we have. And, it's actually kind of humbling to see, like, wow, I actually had a part of some of those missions. And, yeah, I never thought I would get to work on something like this. So, and it's because of my experience here at Boise State, and my upbringing and passion for technology and engineering that has enabled that. So, lots of celebrations. It's a lot of hard work. And I had my moment of excitement. This was landing night for Curiosity back in 2012. I was in the mission control area for the surface mission. So we were waiting for the touchdown signal, and then we would take control of the rover and start the surface mission. So this was kind of my celebratory thing as soon as touchdown happened. And this was pretty much the highlight of my career. It was so amazing to have so much work and dedication, and actually worked. Watching that sky crane video still makes my stomach turn, even though I know it worked. It's like, I was like, oh wow. So, and during the phone call with the President Obama, I was in the room in the back, and he was calling us from like Air Force One. He was like in transit, and I was like, oh wow, he's actually paying attention to what we're doing. It was I thought that was really cool. So one of my major contributions to the Curiosity rover program was working on the ATLO team. This is the assembly, test, and launch operations phase of any flight project, where you finish up the design and then you take actual parts that you built and have to integrate them together and test it to make sure it'll survive the environment or planet that you're sending it to. So we get to basically assemble the spacecraft, and this is a picture of our ATLO team in Florida. I'm the guy in white. And this is shortly before launch. You've got the spacecraft on the floor there, ready to go. It's in its fully cruise and launch position. And behind it are the launch fairings. So these are the basically the nose cone of the rocket that protects the spacecraft during ascent. And what I think is cool is how big these are. Like, your spacecraft is this tiny little thing. You have this like 30-plus foot fairing that encapsulates it. And it's amazing that you need that much power to send such a small thing all the way to Mars. This is kind of a fun picture. One of the things I worked on in particular was the spacecraft baseline test. And this was my charter to verify that everything we plugged in worked. So I had to verify the copper path, or every wired connection in the spacecraft, was integrated properly. And so this involved writing software tools, frameworks, and automation techniques to power on every device at various phases of the assembly program to make sure things turned on, make sure the telemetry came back okay. And it was kind of one of our sign-offs for launch to say, yes, we tested every cable copper path we did, and we're good to go. So this was a fully automated test. It was probably some 5,000 lines of code, and it was a big feat that we were able to use on another mission later on that I worked on. One of the cool things that I get to do is work with a lot of really smart people. I love surrounding myself with people that are smarter than me because I learned so much. And these are my two of the leads. I'm the guy in blue. And there's the two of my leads on the ATLO team. This were a few days before the final assembly of the rover. We were doing some robotic arm testing in the clean room. This is an image of the spacecraft when we attached the heat shield to it. The heat shield is what protects the spacecraft during entry, descent, and landing. And this was the last time the wheels saw the light of day. So this is kind of a final farewell to our rover that we love so dearly. This is us standing underneath the back shell. So this is the thing that protects the descent stage in the rover system during its flight to Mars. And there's holes in the top because that's where the guidance rockets will vent through. And we use those rockets during entry to do actual guided entry. The spacecraft was flying through the atmosphere autonomously. It wasn't just ballistic, shoot a bullet to Mars and hope it lands somewhere. We actually had active guidance control, which is a first for a Mars mission. So you can see the back shell is quite large. You can stand underneath it. It's about the size of the Apollo capsule. One of the things that I'm really proud of that we got to do, engineers love to sign their name on stuff and let's I made this sort of thing, but this was more just paying tribute to the space program, and we got to actually sign a little decal on the rover, all the people who helped build it, and then later, actual image from Curiosity on the surface of Mars of that decal with the Martian soil in the background. Like, whoa, my name is actually on Mars. I still have zip ties and everything. Yeah. So one of our final farewells that the ATLO team does, we go to the very top of the vertical integration facility, or the VIF, and that's the nose cone, those fairings that were fully encapsulated, and this is kind of our final farewell to the actual rocket. And a funny story, when we were building Curiosity, this was actually a really fun summer to be at the Cape Canaveral, because it was the summer of the very last shuttle launch of Atlantis. And so we were testing the rover about 5 or 6 miles from the VAB, Vertical Assembly Building. And the rover was still powered on, and the launch of the last shuttle launch was like less than 30 minutes away. And so we're powering down the Curiosity as fast as we could so that we could all run out the door and drive, safely to the VAB, where we got to witness the final shuttle launch, and it was amazing. It was probably one of the most impressive launches I've ever seen. It was so much power and force, and to know that was the last one, we're very lucky to be there. And then Curiosity, shortly after that, had its successful launch in November. We actually hit our first launch opportunity, and it was really kind of surreal when you're doing the countdown, because you're so far away from the launch pad. All you see is a picture on the TV screen, and you're looking at telemetry, making sure the spacecraft is fully configured, all the power levels are right, the batteries are online. And then you do the final countdown, it gets to less than 5 seconds, and we're like, well, I think it's going, we better go outside, and we're going to miss it. So about 3 seconds before liftoff, we ran outside and just had enough time to see the rocket go up over the tree lines, and that was it. That was pretty cool. So after launch, the rover had about an 8.5-month journey to Mars. So during that time, what we do, just like good software people, you ship it and then fix all the bugs, right? So you can't really change anything hardware-wise, but we still had opportunities to fix the software and complete the software. So we launched with enough software to do the landing nominally, and that's about it. So I couldn't really do a drive around or anything. That's okay, because we're getting pretty good at doing software patches from millions of miles away. But I joined the EDL team to work on the sky crane and landing system. So we were basically had to come up with these kind of hellish scenarios. What would happen if we lost a flight computer during landing? Can we survive that? So we're going into the test bed and killing computers and taking out power modules mid-flight. And the way we did that was using our test bed analog. So we build a double of our spacecraft so we can test it here on Earth. This is the vehicle system test bed. This is where we test the rover in our Mars yard scenario. So it's not actually, there isn't actually a garage on Mars, but there are these rocks that we use to simulate the environment. But for the EDL system, this is what our spacecraft simulation looks like. Just a bunch of racks on a computer. Probably looks like someone's messy lab or the back of your home TV entertainment system. We actually have flight copies of all the avionics, the hardware, the boxes, and we put them on these desks and we wire it all up. And this is kind of an agile way where we can change components and swap out boxes. But this is simulating the entire landing sequence, the real hardware, the real commands. We have racks that are designed to simulate the solar system and the stars for the scanners. So this is where we ran all of our tests, and we did thousands of these. I did about several dozen during just the time from launch until landing. So we were building this rocket jetpack separately. This is what actually went, but we never tested it because we were sure it was going to work. So doing a full up system test of the sky crane maneuver was not practical from a budget point of view or technical. And so we had a lot of bets on our systems engineering expertise that we could actually build a system at the subsystem level, integrate everything together, and trust that it would work. So we had to test every subsystem independently. The thrusters, the rockets, the radar in particular was something we built in-house that we had to test. And that was kind of a fun test because we flew it on a helicopter. It was the same helicopter they used to film the Series 24 because it's LA. But so they flew it around the desert to measure some of the slower rates that the spacecraft would see during entry. But then we strapped it to an F-18 and flew it at a mountain side. The pilot was pretty good, but just to get more flight-like rates, closer to the rates we would see during entry. So then this is the configuration during entry, right before the sky crane maneuver happened. This is artist rendering. And as you know, you can see from the videos and from history that this actually worked. And so it was actually pretty cool. And a few days after the landing, my wife had bought me this really cool experience. So Curiosity can't have all the fun of using a jetpack to go fly around. I just had to do it myself. And so we went to Newport Beach and did this thing called Jet Lab, where you can actually fly around in a jetpack, but have a one of those little jet skis following you around, and you fly above the water. It was fun. So I met my wife down there in Southern California, and she's been so supportive of everything I do. Unfortunately, she wasn't here today, but she's just been a real believer in space. She's a teacher herself. She also works at Disneyland. And so she's always been there and really supportive of all the talks and work that we do together. So then we land on Mars, and of course, what's the first thing you do? You want to take a selfie, right? That's what people do these days. So here's Curiosity actually doing a selfie. This is an actual picture that we took on Mars with Mount Sharp in the background. That's a 3-mile-high mountain in the center of this crater called Gale Crater. And I'll tell you a little bit more about how we take these selfies as we go. But working the surface operations mission, the first 90 sols, or days on Mars, we had to live on Mars time. So a day on Mars is about 40 minutes longer than a day on Earth. And so in order to maximize your daylight hours of operations on the surface, you actually have to match your schedule to kind of follow what Mars is doing. And this was weird, having to get up 45 minutes later every day. And it got old pretty quick, but it was also really fun just being completely in lock sync with what your robotic explorer you built is doing on another planet. And it was governed by this relay network. So Curiosity's on the surface, we don't send all the data directly back to Earth. We go through the orbiting assets that we have around Mars that you saw in the video, like Mars Odyssey, the Mars Reconnaissance Orbiter, and Mars Express. And then this comes down to the Deep Space Network, which is a series of 3 antennas we have throughout the globe that receive data from outer space, particularly deep space, anything past our Earth-Moon system. And so these are like big 70-meter antennas out in the desert. 70 meters, that's quite large. And then we get to work with the data from there. So I did this for several months, and it was pretty exciting working the day-to-day operations of the rover. And early on in the mission, we actually met a lot of our base mission objectives, working with the scientists, them wanting to go look at interesting sites and see where they wanted us to drive the rover. The engineering team was responsible for the health and safety and operation of the rover, and the science team was responsible for looking at the pictures and saying, go there, and we would do everything we could to accommodate that. So one of the initial discoveries was evidence of this ancient water bed, this flowing water about knee height on Mars several millions of years ago. And just by looking at the images, the scientists were able to say, yes, there's no way this could have formed any other way. I thought that was pretty amazing. So then we took a laser with us and used this laser to do science. Sometimes someone says lasers and Mars, this is exactly what they think. It's 100% true. So we took a remote sensing laser where we could actually blast the surface of the rocks, vaporize them, and then take an image of the ejecta and analyze what that rock is made of to decide if it's something interesting enough to go drive to. So this is actually what it looks like, but without the red laser beam and the bright light. But it's just a pretty benign activity. You can't see the beam or anything. But during testing, it was always fun during the ATLO campaign because we'd have to put on these special laser grade optics just to even sit behind a computer and operate it. It's kind of funny. But every space mission comes with its risks and anomalies. And just like any engineer or science person, we love to solve problems. So, and fortunately, this wasn't a major problem, but on Sol 200, Curiosity had a fairly major anomaly where the computer stopped responding. And that's bad because if your computer's not responding, then it can't shut down and recharge its batteries. And if the batteries don't recharge, then your power bus browns out, and then it's just bad. So we saw this in the telemetry early, it didn't honor the shutdown command, and we were able to send a command kind of last minute to power off the prime computer and power back, and which would basically tell the backup computer to automatically turn back on. So that was kind of a Hail Mary command that we threw, and it actually fixed the problem, and we were able to do diagnosis on the backup computer, or the faulty computer, during the operations. So since then, everything's been going well. We're on the backup computer, and but this was definitely a day of worry. Also, the wheels started showing signs of fatigue, and particularly these large holes started appearing. We actually put holes in the wheels intentionally, and if you look at it, the back wheel here actually has this hole pattern. It actually spells out JPL in Morse code, because again, one of those things about sending your name somewhere. But we started noticing kind of anomalous holes in the wheels. And these wheels are made of aluminum, a very thin aluminum, so it's like popping a hole in a pop can, and you can't really fix it. So we started noticing these, and then basically replanned the path to Mount Sharp so we drive on more soft soil. And now we're to the selfies. So this is kind of cool. It's not only is this fun, but it's also a way for engineers to assess like how much dust is on the top of the Rover and the top deck, and see how the hardware is eroding over time. So you notice there's no robotic arm in this image. The camera is actually on the end of the arm, so it's kind of like a selfie stick. And it's not just one image. So you see these selfie images come back, and it's actually a series of hundreds of images stitched together. So all these jagged edges are rotations of the arm. We're backing out the rotations from the kinematic model, and then actually stitching together the image. And all this stitching happens in the cloud. We use Amazon's cloud computers to build all the big mosaic images you see. This is the most recent one from Curiosity, where this was taken less than a month ago, where we stitched together all these pictures to see like kind of an under image of the rover fully together. We usually do these at kind of the significant sites, like the first drilling site or the first significant scoop site. In this case, it was this rock formation over here that the internet has apparently been finding evidence of life and aliens, and claiming that it's a big cover-up. But at the end, it's just rocks and dirt. So we haven't actually found any significant signs of life yet. But Curiosity's there. She's all by herself, but says hello every now and then. So shortly after working on the Mars Science Lab, I moved on to do the ATLO campaign for SMAP. This is a Soil Moisture Active Passive mission, which was a remote sensing mission to map the soil moisture of the globe every 3 days for about 3 years. And so we actually used some of the hardware from Curiosity, the same flight computer, some of the same power modules. And so it seemed like a good fit to go and do what I did again, which was the baseline test and assembly, launch operations, do the countdown. And this is a pretty interesting spacecraft because of how it does its sensing operations, which I'll show a video here in a second. But that's the spacecraft in its launch configuration. All of the deployables and antenna, solar panels, and everything is all folded in, ready for launch. And we launched on a Delta II rocket from Vandenberg, California. So it didn't have the Florida experience, but it's more of just a few hours north of Pasadena. Here's a short video of kind of what SMAP was supposed to do, which I'll get to eventually. I'm going to annotate it as we go. So after launch, you can see the same fairing gets ejected and exposes the spacecraft, and then we get a second burn to get us into the orbit. And then we actually separate from the upper stage, and this begins an automated series of sequences that deploy the solar panels. And this was a really fun time because we actually saw this video from the upper stage. It actually had a camera, so as I was pulling away, we could see the solar array deployment. And this is done with a series of springs and explosive bolts that actually separate the hardware that are activated by electrical signals. And so it uses solar power to get its energy from the sun, and it has thrusters to stay pointed at the sun, as well as mag torque rods. It uses the Earth's magnetic field to align itself. But this is kind of the business end of the spacecraft. We have this antenna that deployed on a boom. This boom is really large. You can't really cram it into the top nose cone of the spacecraft, so we fold it and then have a motor, like a winch, that drives it out. This whole process took many days. But then we kind of bloom the antenna, and it's kind of in there like an umbrella, and it opens like an umbrella with a winch. So we drive it out with this motor, and the whole thing is about 20 feet wide when it's fully deployed. So this lets us use a powered amplifier that you see at the bottom there, the little horn, to actively send a signal down to Earth, and the reflected signal is what gives us soil moisture. But just having the antenna stationary doesn't give you the full resolution, or it doesn't let you cover the entire globe. So we spin up the spacecraft, and then during this time, the lower half of the bus, the spacecraft bus of the body, is stationary. So we're using reaction wheels, big rotational masses, to stabilize the base of the spacecraft while the upper stage is spinning. It's pretty interesting mechanical coupling, and as well as the control mechanisms to do this. So now you can actually scan the Earth and build a high resolution map of soil moisture over the entire globe. So we use algorithms on the ground to match the radiometer sense data with the active data to figure out soil moisture. So this whole thing took about, we spent several weeks, almost 2.5 months, just doing the initial checkouts of SMAP. And that was, it was a long time, but we actually did it quite efficiently. And then we started doing science. And so we got about a month worth of good science data mapped. And then the radar stopped working. So the thing that's actually pinging the surface and getting the active part of SMAP stopped. It didn't turn on anymore. And so SMAP has a polar orbit, and we flew over this part of the orbit called the South Atlantic Anomaly, where our electronics just started going haywire. And usually you try to plan for this, but you can't always anticipate all the things you'll run into on orbit. And so we spent the last 2 months trying to debug the problem. How do we get the radar back on? You know, what happened to the mission? And earlier this week, they announced that it's gone. So we weren't able to recover it properly. So this is actually really sad because you spent a lot of time on this mission, and you're expecting a 3-year return on science, and now this thing you put all your time into doesn't work anymore. So the team morale was pretty low, and it was not good. But on the good news, you know, the science team was able to determine that the radiometer piece of SMAP, the P of SMAP, passive, is still fully functional and quite high resolution. So we can still get kind of a lower resolution of soil moisture just by listening to natural reflections off the Earth. So keeping on my journey through the solar system, back here on Earth, I took on a role shortly, kind of during SMAP, as a data scientist. And this was really taking everything I'd learned from the projects I've worked on, data sets I've seen, and using my computer science background that I learned here as well as in industry to really make sense of the data. How do we make better insights of our data and enable useful self-service analytics tools for engineers at JPL? So just by a quick show of hands, who here is mechanical engineering on the mechanical track? And awesome. What about the computer science? Oh, good. This is great. So this is really kind of focusing on my computer science skills, but also my systems engineering skills. The reason why that is data science in particular is kind of a Venn diagram of data science. And you need to have some hacking skills. That brings a lot from your computer hacking skills, as well as just knowing how to work with data. You also need substantial expertise, so like subject matter expertise. And then it's also intersected with math and statistics. And that intersection gives you kind of data science. Anything else is not quite, you can see the danger zone there. That's like your people hacking target or whatever. But, so these things combined is really what gives us these capabilities. And working in the cloud is what enables a lot of this rapid innovation. This whole big data stuff and data science in particular has to move very quickly. You know, some of the V's of big data are volume, velocity, variety, and veracity. And so you need to have infrastructure available to even work with the data. So if you can't even look at it, if it's trapped in some database somewhere, if it's on paper somewhere, you're not going to be able to do real science on it if you can't even compare it to other sources. So JPL actually worked with Amazon to build the GovCloud region. And so This is a place where government, or just really ITAR, which is a compliance type of data or measures, to build a region in Amazon where we could do this kind of rapid prototyping and innovation. And so in the background there, that's what a data center looks like. That's actually one of Google's data centers. But so now you can imagine harnessing the power of this data center. You don't have to build it on premises, but you can do it and let Amazon build your data center and really take advantage of this elastic compute, elastic operations. And this forced me to learn. Actually, I did this kind of on my own. I'm always learning new things and trying to accelerate my knowledge and put more things in my toolbox. But these are some of the technologies we work with. And if you recognize even half of those, that's great. Or all of them, that's even better. So data scientists are always, this is part of the hacker side, where you always have to go and learn the best tool for the job based on what you're doing. If you don't have the tool you need, you either go write it or you learn it. So these are some of the technologies that we use. This is stuff that may be cutting edge, may not be tied to the usual government release cycle of, okay, it's an industry, we'll let it bake for a decade and bring it in or something. These are software tools that are being developed within the last year or less that we can use. So one of the big things with finding data is how do you access it? You go to the library, you can look up a book, or really in these data sets, they may be spread out through many silos of data, relational databases that take fairly specific queries in order to figure out where things are. So one of the first things we realized was we need to do search and take the technology that's been built by like Google and Twitter and Facebook, and how do we actually build that and make it useful for JPL? So we started indexing a lot of our silos of data into searchable databases, and this really unlocked the data sets to let us then hack on them and make useful things. So one of the products I made recently is we call Streams. And Streams is a way that we use a lot of technologies in the cloud to build a system that will let engineers do their job faster and make real insights about their data. So for the Mars Science Lab, we get this thermal telemetry. We have sensors all around the rover, and it's collecting data like what the temperature is on a particular zone or set of actuators. And this would be a trend of about a year or so of data. And this involved a very cumbersome process, from getting data on the ground, querying it out, putting it in Excel, breaking Excel, trying to reduce your data set so you can finally generate this PowerPoint image that you can then email out to your colleagues and be like, here is my trending report. And as soon as your colleague asks, well, what about that one little point there? Like, oh no, now I have to go through this all over again. So, like, no, this is not acceptable. Right? It's NASA. We're gonna fix this. And so, built this prototype called Streams that lets our users interact with the data and explore it in real time. So this is using search technology to enable the searching of telemetry, where users can now drill down to data points, or just by the click of a mouse, like you're exploring your stocks, explore a half a year or even the entire data set. And queries are happening in less than a second, rather than having to take many days or hours to get data out. So this lets our thermal engineers and operators explore the data in real time, isolate the problems they're interested in, and really explore the data set. You can see the min and max temperatures over the course of a Martian year. You can drill down and examine it. But now, rather than sending a PowerPoint to someone, they just send a link. I mean, that's how we do things nowadays, right? Sending links around. So now you can say, hey, here's my plot, and you can send a link. As soon as the person clicks on that link, now it opens up for them the same exact experience. For interacting with the data, they can now ask their own questions, do their own trending, and make their own discoveries. We integrated other data sets using search. This is event verification records. You can search through and see the log messages that the rover generated during that day or the entire mission. We also indexed the image data set. So now you can see correlations, like what was the rover doing when this temperature was examined? Was the robotic arm creating a shadow that was causing the zone to get cooler? And so adding context to data is one of the tools that data scientists use to help make discoveries. We had to build a data pipeline using modern tools. We get data from the Deep Space Network. We flow it through Amazon's GovCloud. And we use tools like Apache Spark, big data technology that's kind of changing how data is worked with nowadays. And then we index that into our search cluster, which then gives our engineers the ability to interact with their data in real time. And this all happens in just within minutes of data coming down from Mars. So again, we're using the cloud technology, built on some technology called Mesosphere, which kind of abstracts your data center into a elastic compute instance. And then we're using Docker to containerize all of our processes and computing, and all that's running on Elasticsearch. So this is kind of a stack. This is what you get in your distributed systems course here at JPL, or not JPL, here at Boise State. So this is kind of the systems part. So data science in particular is interesting because it's not just statistics. It's not just computing min-maxes and standard deviations of data. It's actually systems work. The hardest part is wrangling your data into something that makes sense so you can actually use it. And that sometimes involves building stacks that run in the cloud. One of the key things that not only has helped me as an engineer, but helped our culture of innovation is sharing everything. Raise your hand if you've heard of GitHub. Yeah, awesome. It's the most collaborative, amazing tool that engineers have at their fingertips today. So we use GitHub Enterprise, which is just a self-hosted version, to share all of our code. We make our prototypes, we build these big data systems, and then we immediately share it to everyone. And so we did that prototype of streams on MSL. Well, I was able to find the code on GitHub and port it to the SMAP mission in just a few days because it was open and available. I didn't have to go bug someone. Can you please send me the source code? No, it's right there. So this is what kind of enables a lot of this rapid innovation and infusion. So let's talk about a little bit about your journey as students who are considering working, in engineering and working. Eventually, you're going to end up in the workforce. How can this stuff help you? Well, like I said, what do you have in your toolbox? When I was a student, one of the things I constantly remember and I go back to in my head is, what was my favorite part of learning here? It was seeing a lot of different things. And even if it didn't apply, like the elective courses, or even stuff in chemistry or physics that I don't actually use day to day, working with systems engineers and seeing different data sets and instruments on the spacecraft, I actually had a familiarity. I'm like, I kind of know what you're talking about. I can understand the language. And that was a starting point to do this collaboration of now how do we make sense and solve your problems, because I can actually understand what you're talking about. So filling your toolbox with things that are meaningful is really important. And one of the things that I emphasize is doing extracurricular activities. So this involves things like the microgravity program, doing aero design, getting involved in any way you can outside your classes. We'll give you some of the most real-world examples of what it's going to be like in industry. And this actually doesn't stop when you graduate. One of the things I realized that I needed to do is when you get into a job, you kind of get really focused on what you're doing. And there may not be a lot of opportunities to continue to grow and learn new things because you're not in class anymore. So as a professional, now you really need to do that by yourself. And so going to meetups within your local area, listening to what other people are working on at different companies, or even within your own company is really important. Going to conferences, even if you're not presenting, just going and hearing and seeing what's going on is huge to advance your own skills. This is something that resonates with me a lot, and that is doing something that matters. I see this a lot, especially from this computer science angle. I'm not trying to narc on Silicon Valley, but some of the smartest minds in our industry are trying to figure out ways to make people click on advertisements more efficiently. Like, that makes me so sad because, the Twitter, the Facebooks, it's like they're working on real systems, but does it really matter, I can say that, working in government, you're not going to get rich. We don't get paid the Silicon Valley wages. But we do get to say, hey, I sent a robotic rover to Mars. That's kind of cool. So you're what you take home every day and what really sets in is that I'm working on something that actually matters. There's a program through the U.S. government called the U.S. Digital Services. There's another one called 18F. And this is, if you guys remember healthcare.gov, when they first released it, it was a complete disaster. It did not work. It was like a train wreck of a software deployment, anything. and took forever to build. So government realized that, and they formed this U.S. Digital Services to go fix that. And what they did is they brought in the experts who were good at building those systems, you know, from the Valley, from Google, and they're like, hey, come do a tour with the U.S. government, and let's go into U.S. Sites like healthcare.gov and fix these problems. And you do that for like a year or 2 years, completely revamp and make it modern, do it right, and then they get out and they get to go back home. Well, I saw an interesting blog post from someone who just finished their tour at healthcare.gov, and he was like, man, I came back, you know, he worked for the immigration office and really modernized their systems, helped them go paperless, really transformed their processes. And he went back to Google, and he was like, it was kind of surreal. He was like, I go from helping this, feeling like I made a difference in contribution to my government, and now I'm back at Google, you know, working on different protocols and hearing people in this lush environment. I have free food and everything, and I get to work on the cutting edge of internet protocols. But what does that really matter? And he almost left Google after that, but he was able to find a way he could innovate in a developing country with Google technology. So people starting to realize that, but that to me is something that really resonates. Real world projects, you can't really finish them in a semester. So, you know, that's why doing extracurriculars really give you an insight for, you know, this thing's going to continue for a long time. Our space missions, like Curiosity, take, you know, a decade or more just to build and complete. And so seeing a project from end to end may take a long time. And seeing just during school, you only kind of see one little aspect of it. So having work on long tail projects is really useful. Learn to use or make new tools. This is something that really, it goes back to some of that collaboration where you go to meetups. If you don't have a tool on the job, don't be afraid to make it or bring in a new one. A lot of industry, especially aerospace, kind of gets set in the ways of, okay, these are the tools we have, this is what we use, but we've always used it. But taking just a little entrepreneurial effort to bring in something new, prototype it, show it in a low-risk way, you can really not only expand your own horizons, but make a big difference in a large organization. And then collaboration. This one's always my favorite because we started we have GitHub Enterprise to share our work with our colleagues and also external partners. But we started this open developer meetup where once a month we invite developers and other people. We had mechanical people and people building catamarans come in and share how they're using technology with the rest of the lab. And oftentimes it's like you hear other people saying, hey, I'm doing the same thing. You know, I built the same thing you did. And then suddenly they're collaborating and making each other's projects better. But we've had the great speakers come through. I'm usually sharing something once a month, and it's a great way. It's kind of like a meetup within your industry. All right, so this is kind of my journey from BSU to Mars, and it's really been an exciting journey. I can't wait to see where it takes me. And I can't wait to see how you guys can really take what you learned here at Boise State and all the opportunities it has to offer to have an exciting and meaningful career. Thank you.
We have some time for some questions.
What languages should I learn?
What computer languages should you learn? I love this question because so I generally say when someone says, you know, what's your favorite language or what's the most important programming language, my response is whatever is most applicable for the job. In general, though, there is kind of one I go to, and that is Python. Python is just very easy to learn. Okay, I saw one place recently said Python's a new basic, and that was kind of an insult to Python, but at the same time, it's kind of true because it's very powerful, very useful language that any discipline can use. This is in this world of modern engineering. If you don't know a programming language, you're going to fall behind very quickly because you're going to be generating data that you need to be able to transform and make sense of. And having a language like Python under your belt is really a good gateway to building on other languages, whatever is useful for the job. Yeah.
When you're part of Stream, was that something that your stack was solving the problem, or was that so much like y'all were implementing algorithms to get that query down to like real time and this is a second?
Good question. So with Streams, that was a prototyping experiment that we actually did in 2 weeks, and we were looking at technologies available today like search, and applying that approach to this problem of real-time time series data. And it happened to work. So, but basically, we're using these technologies that have already implemented a lot of the algorithms for doing some of these real-time calculations, but we had to write some of them ourselves. What's basically happening under the hood is just doing an aggregate over time and then finding min-maxes within these aggregate buckets of data. And so building those queries is like writing your own algorithm to do that. And so that combined with the stack that enables access to the data is really what made that possible. So most of the coding, though, was on the data pipeline, kind of the plumbing, as well as the visualization, getting the interactions just right for users.
So you write the queries you wanted, and then the tools should speed it up.
Yeah, the tools were there to make the queries execute faster and smarter.
So with when you were designing Curiosity Rover, you mentioned technologies, and modern electronics are very sensitive. So how do you go about making sure electronics on the Curiosity Rover are space worthy?
Good question. So there's a whole industry. It's not a very big industry, designed around or focused around making radiation tolerant hardware. And it's generally a few orders of magnitude more expensive than the off-the-shelf hardware. But they do things like triple redundancy at the transistor level, all the way to special protective coatings on and how you package the device. So you can only do so much there, and that will get you most of the way. But generally with a space mission, because some of that is still unknown and very expensive, we just send another copy of the hardware. So that's why there's like 2 flight computers, 2 power modules, and 2 everything on a spacecraft. So when one has issues, you always have a backup.
This is another question about the Mars Science Laboratory. You said you had like a duplicate rover here on Earth. Was that equipped with an identical RTG like the Mars rover, or was that powered from a grid source?
Good question. So about the rover and how was it powered here on Earth? So our stud double, her name is Maggie. She didn't have an RTG. The RTG was built at INL here in Idaho, and it actually never went to California. It met its spacecraft in Florida. But Maggie never had one. So it uses we call it an umbilical cable that has all the power and telemetry into the back where the RTG would go, and it kind of tugs it around as it grows. So it also has batteries, same batteries.
I've been following your career for a while now since I was in high school. So it's been really exciting to see where you've gone. And it was kind of cool that I followed you some when you went to Gravity last year and then also
Oh, you're from Yale, yeah.
but I was really interested in, so you had your internship at ATLO in school. Did you have a different plan before you got your internship at ATLO? As far as where you're going to go?
Did I know where I was going to go before my internship?
Yeah, like did you have a different plan? Was it NASA or was it something a little bit?
I didn't actually know. I knew I loved engineering and working with computers and programming, but it's really that internship that made it very clear. Before that, I was just doing startups here in Boise, ran a company called Cradlepoint and some other small startups. So it's either that or go to Micron or go back to HP. So I didn't actually know I was going to end up at JPL before my internship. So during the internship, we'll open up possibilities we weren't even aware of in areas that may not even be here in Boise, even though I do miss Boise dearly. Yeah.
So you mentioned there's 3 deep space networks around the globe. So how do you manage data recovery from your Curiosity rover when competing with other space agencies around the world? Because you're not the only one.
All right, we are. How do we compete with other space agencies? So Isla is another Russia, but we're the only ones with the Deep Space Network. So we're usually the primary asset for doing deep space communications. We actually help other agencies with their data, like the Rosetta mission that landed a small lander on a comet, not long ago. We helped them get their data back. We worked with India when they did their MOM mission and did the relay for their data as well. And so it really is some level of partnership, but we definitely help and share this asset with where for space missions?
Yeah.
We do. It's a pretty custom protocol, but it's called CCSDS, and it's a packet encapsulation method that's been used over the decades to properly frame data packets that come out of your spacecraft and actually arrive in the Deep Space Network. And so DSN knows how to unpackage these data sets and then ship them down the line. But there really is no TCP networking in space. We don't have an interplanetary internet yet. We did an experiment called DINet where we actually did a TCP level routing protocol and algorithm across like 4 different assets. It was like Mars Rover Opportunity and like MRO and Deep Impact spacecraft. We like relayed some data in a TCP fashion all the way through as a kind of a proof of concept. So that worked. But that would be great because one of the main constraints you have with operating the Deep Space Network is everyone wants to use it, and it can only point at one point in the sky at a time. So in order to move it, it becomes this scheduling nightmare. So if we had more intelligent routing methods, we could make better use of the asset. Yeah.
How important was international collaboration to the missions on which you worked?
How important were the collaborations with international?
Yeah, like did your missions do any, or was it something that was just all U.S. led?
So typically, a lot of the main work happens here in the U.S., like the spacecraft, NASA said, JPL, will build the Curiosity rover. But the payload, the instruments that fly with the spacecraft are competed. So different agencies and companies can actually compete to have their instrument fly. And so one of the instruments was built by Russia. The ChemCam laser was built by France. So it's a very collaborative environment. And when we were working surface operations during the day-to-day planning, everyone would chime in from their remote centers and report on their instrument and what they wanted to do. And you hear like accents from all over the place. So it's like, wow, I don't even know what that guy said. But it was awesome. Okay, but I think he's got his stuff in, so we're good to go. But it was pretty interesting getting to see all different parts of the world just through one mission. Yeah.
For the moisture sensing project, when that failed, is that kind of the project, or are there plans now to try and make a better one, improve upon it, try and figure out the recovery system ready to make? What are the plans for that project?
Right. What's next for SMAP?
Yeah.
Probably SMAP 2. So the scientists were able to repurpose the mission from a radiometer point of view. Rather than using the active part of SMAP, we're just going to do more passive listening and try to do the best we can with that. Going forward, it's going to definitely impact what we do for the next SMAP, if there is one. We may fly another radar instrument or a secondary power amplifier. So when the first one goes, yeah. So those all have budgetary constraints and weight and mass considerations for launch. And so, but yeah, the mission's definitely not over. It felt like that for a while, But fortunately, we work with a lot of smart people, and working with the collaboration of scientists and engineers, came up with a pretty clever method to repurpose the mission.
More. Do you have to worry about or security in your communications with extraterrestrial devices?
Do aliens hack our spacecraft? We definitely take security measures to make sure all the data transmitted is at least safe, if not encrypted. Having it be a U.S. asset drives a lot of those constraints and policies for operations of the asset. So it's also to some degree security by obscurity, meaning like, oh, well, no one else has a 70-meter antenna they can blast Mars with. But at the same time, we do take precautions for, especially the commanding side of things, to make sure commands are sent in a safe way. Kind of a funny story with the Spirit and Opportunity spacecraft. So every now and then, Mars is on the other side of the sun as Earth, and we call that conjunction. And that usually lasts for like a month or so. And during conjunction, you can't send commands or get data from your spacecraft. So we did an experiment during one of the conjunctions where I wonder how long we can actually transmit before the sun gets in the way. And so we're sending these benign commands, to the spacecraft repeatedly, trying to see like when it dropped out. And during that time going around the sun, it actually corrupted the command and turned into another command. And we're like, oh. And so, okay, we're not gonna do that again. But interesting ways of things can happen in flight. Curiosity's been through 2 conjunctions now and came out on the other side. It was fine.
Any questions?
So you mentioned that during this conjunction, how many autonomy rules does Curiosity have?
So how autonomous is the space for the rover? It's as autonomous as practical. So we do a lot of manual planning of its overall path. During conjunction, we don't do any driving, it just sits there and does passive science observations. But the spacecraft has a fairly good deal amount of autonomy, but it doesn't have a very powerful computer. It has like a space grade Rad 750, it uses to like control missiles, but so it's fairly low power processor, but good enough to do something we implemented after landing called vision mobility system, where we now have this kind of auto nav way where we do the rough plan and then we tell the rover to drive, and it will drive like 10 meters, stop, take images with the stereo cameras, analyze the surroundings, and then if it's still safe to go, it will keep driving. So that's kind of how we let it drive by itself, and if there's like a big rock in the way, it'll actually replan around the rock. So we can do that on fairly old hardware.
What's the time lag for communication?
That's a wonderful question. So the time delay, yeah, you're sending a signal at the speed of light, many millions of miles, and it varies. Usually it's between 5 and about 20 minutes, depending on where Mars is. And so we had to take this into consideration every day. One of my jobs was working surface was the engineering uplink lead, and I had to basically make sure we knew exactly how long it would take for the command to go out the horn of the DSN to arrive at the spacecraft. And so I had all these calculations. You're going from like Mars minutes to Earth minutes, and it's like changing every day. You kind of see it go up in time. You kind of know, is Mars going away from me or coming at me just by seeing the drift in time. But it's also an interesting thing because during entry, set, and landing, the time delay was about 15 minutes. And so by the time the rover touched down, was all safe, that 7 minutes of terror, had already happened. It was already dead or alive by the time we even heard it started. So it's it's really trippy working with things that have this huge time delay, which is really governed by properties of the universe, the speed of light. So it's pretty cool. Adds an interesting constant to working with a spacecraft. The Voyager mission has over 12, it might be even up to 14 hours of one-way light time. So it's basically trickling. We still talk to Voyager, and it's like trickling data back at a few bits. And the DSN has to stay focused on the sky, for over half the day, just to get a few bits of information back. That's how far away Voyager is.
Okay, sounds good.
Thanks, guys.